Okay. Good morning, everyone. Hope everyone is doing well. We have a cold spell on the East Coast, but hopefully everyone is warm. I'm going to talk for just a couple of minutes to give people a chance to join. My name is Mircea Stan. I am the editor-in-chief for transactions on VLSI. This is actually my fourth and last year as editor-in-chief for transactions. Um, I'm looking for, it was a very, um, interesting time, I learned a lot. I hope I gave a lot. But it's time to move on, and I'm looking forward to assist the next editor-in-chief. One of the initiatives that I've done for the transactions is this series of talks where we try to pick you know the papers that are more interesting, that are a little bit intriguing, where we think the community would have things to learn from, and have a series of webinars. And we've had them relatively regular, but we are probably going to increase the rate at which we have them. So maybe every other month. So please, stay tuned. So now, without further ado, it is my pleasure to introduce Yousef Safari. He has a PhD from McGill, lots of research interests related to heterogeneous integration, 3D packaging, EDA. He works for ANSYS now, which is really part of Synopsys, and he has several awards, the CAS Predoctoral Grant, Fellowship, and McGill Doctoral Award. And he's a member of IEEE, the Packaging Society, and the CAS, Circuits and Systems. So the talk is based on a transactional VLSI paper, and is a thermal simulator for advanced packaging and chiplet-based systems. And he's the first author with a few co-authors, and Boris Weisband as the advisor. Yousef, you have the floor.
Uh, Good morning, everyone, and if you are in the east side, good afternoon. Thank you, Mirko, for the introduction. And so yes, today I'm pleased to present a recently published paper in TVLSI, Thermal Simulator of Advanced Packaging and Chiplet-Based Systems. One of the works that I was doing during my PhD at McGill. So this research is supervised by Professor Boris Weisband, who is currently at UC Irvine. So the roadmap or the path towards the heterogeneous integration, which is supported by several factors in the past couple of years and maybe decade ago. This is there's a significant the main probably motivation on the technical side is that there is a significant scaling gap between the package and on-chip features. So the performance benefits that we were getting from the device and interconnected scaling is not as much as profitable as before. And now the package is probably the key for performance scaling, where we can get benefit in terms of the latency, bandwidth, energy per bit, and all those metrics that essentially at the system level we are caring about. So these novel packaging approaches, they support essentially, if we look into their key features, probably the common feature is supporting heterogeneity. And this heterogeneity can be in terms of the material, in terms of the components of the platform, and it also can be in terms of technology node that they are using and combining together to create the system. And so the main point here is that we are moving from a single node fabrication or homogeneous design towards a completely heterogeneous realm of system integration. And these novel platforms, they are promoting a chiplet paradigm, a path that is essentially the semiconductor industry is essentially looking for. And given several factors, financial, technical limitations that we have for the system on chip design, which essentially brings us a significant benefit in terms of the lower non-recurrent engineering costs, simpler testing, higher yield, and higher performance, of course. But the key challenge here, given all of these good benefits, is that this kind of integration is new to semiconductor industry. So the bottom line is that the entire design hierarchy that we essentially have, or the methodologies, needs to be essentially revisited. And this includes the EDA tools that we are using, we have used to use, especially in terms of the thermal management. So now the reality that we are facing is that we need infrastructure for design as we're moving forward toward these kind of platforms. So as part of this talk, I will first go and review some of these compact thermal EDA tools, both on the academic side and also on the industry side. Then I will dive into what we proposed in this paper, thermal modeling and key features of the ARTSim, the tool that we have essentially presented in this paper, followed by some case studies on different heterogeneous integration platforms, specifically three popular heterogeneous integration platform that we will discuss to show the performance of the ARTSim and comparing it to some baseline to FEM tools, and also where it is relevant to other compact thermal simulators. And followed by some for future research directions and some concluding points at the end. And towards the end of this talk, we also have a Q&A session at the end. And I will take all the questions that are available. So in terms of the academic works that has been done in thermal compact thermal simulation, or CTMs, there are a lot of works that has been published before this work, and also a couple of works essentially that has been improved or extended after we essentially start working on ARTSim, which goes back to around 2021 when we started the project. So among them, we can mention Hotspot. I think they have version 7 also published these days, or 6, which has significant improvement. They also have there is also, which is from Virginia Tech. There is also another extension of Hotspot, which is essentially the parallelized version of Hotspot, packed from Boston University. And also 3D one of the, so probably from EPFL. So probably these three are the most famous work that has been done. But there are a couple of other works that has been great works that has been done in this field. And each of these works, they have different solutions for the solver, on the solver side, on the strategy that they are using for meshing. So different type of input they are receiving. For example, Hotspot, it receives floor plan text files. For packed, it is improved to, for example, physical design files, and the same for the 3D. They can even accept the standard layout file. In terms of the level of heterogeneity, each of them has different level of accepting heterogeneity in a single layer. For hotspot, it's almost limited to single material per layer, and for the packed, the same. For 3D IC, there's a little bit more improvement in terms of the heterogeneity they can support. Per tile, the material can be specified. And also, of course, each of them, as an typically compact thermal simulators or tools for early stage simulation. But the fact, or probably the motivation of the ARTSim at the time that we were developing the tool was a better support for heterogeneity. And I will dive into that, the fact that why, for example, the previous compact simulators were available ones, they couldn't essentially meet the requirements of heterogeneity that we are essentially demanding these days, nowadays. On the industrial side, also we have some compact thermal modeling tool. I mean, the strategy is not essentially this terminology of compact modeling is not that meaning probably that we essentially have in academic side. But there are some tools that they essentially can abstract away some part of the design when they are thermally modeling the system. So I essentially sampled some of them that are much more available, proposed in the or in the market in the recent days. ANSYS RedHawk-SC electrothermal is one of those tools. Cadence side, we have Celsius, and also on the Siemens side, we have Flowtherm. Each of these tools, they have some flows that used for compact modeling. For example, on the ANSYS side, there's cheap thermal models, and also there are some flavors on the other tools. So each of these tools, they have, for example, the capability that you can essentially define to essentially reduce the model complexity. For example, modeling the metal stack from a specific layer above, or a specific, for example, model for the devices to reduce the size of the model. And also some of them, they also have even more compact models like ELFI model support to be generated, which is a couple of nodes in the system to model the whole thermal behavior. And each of these tools are also, they are different in terms of the heterogeneity or granularity of this simulation that they can support. For example, from the device level up to structural level, bump TSV trace level, and component level sometimes, granularity. And so that's probably some of those tools that essentially are available. But again, the engine typically is borrowed from their FEM engine, and the CFD engine is not probably a specific engine that they use for compact thermal modeling, which makes sense given the R&D support that they have from their well-established FEM tools. So with that, I wanted to move to ARTSim, see what we are essentially proposing and worked on as a thermal simulator. So these thermal models that we discussed, these tools that we have shown in the past slides, both on the academic and industrial side, so they are typically defined as a compact thermal models. So this is probably one of those two main approaches that people use for thermal modeling. Either you're using finite element methods or FEM-based, like COMSOL tools or ANSYS, ISPAC, for example, or you're interested into more compact model, which essentially instead of, for example, discretizing the whole system with your mesh to small components and solving, for example, the complex equations of that physics for that specific node, you are solving it for a much simpler model, typically first order approximation. And that's probably the key difference between the CTMs and the FEM tools. Though the state-of-the-art CTMs typically they don't, or at least at the time that we were developing this tool, fully support the chiplet-based platforms. So if you have, for example, TSV units in a substrate or a bridge inside the interposer, that's, or for example, a microbump embedded in within an underfield. So that's essentially the challenge for the tools, CTM tools, to essentially support these levels of heterogeneity within a single layer. And also, this comes to the fact that these tools, they are not able to do flexible granularity for the meshing. So that the support of heterogeneity sometimes it has to do with the approach that those tools are using for the meshing. So we at ARTSim work, we essentially try to support address these kind of challenges. So we claim to support chiplet-based platforms, as well as the conventional 2D SoCs and also 3D ICs. So in terms of the simulation granularity, we can essentially be flexible to give the opportunity to determine the size of the mesh based on the thermal sensitivity of, for example, the block that the user is of interest to the user, and we support heterogeneous material within a single layer. So it means that you can essentially define the heterogeneity in the vertical dimension as well. So the thermal modeling in ARTSim, similar to other compact thermal simulator, is based on the duality that we have between the electrical and thermal domain. If we look into the general heat flow equation, with the first order approximation of this this equation, we get a much simpler equation, which is very similar to what we have in our electrical domain, our Kirchhoff's current law. So based on this duality and the similarity between these two domains, the heat generation essentially, which is shown in here in the Q in this equation, this can be essentially modeled as some thermal current sources in the electrical equivalent world, and heat flow is governed by some by conductance, by thermal conductance or thermal resistors in the electrical world. And the heat accumulation of the system can be modeled with some thermal capacitors, this rho Cp factor that you see. So the bottom line is that we can essentially have at the end of the day, our thermal model of the system or thermal behavior of the system can be modeled as a RC network with some additional current sources. And then so that's very familiar problem for us, solving this spice network and find the voltages, which is the equivalent of the temperature in the thermal world. So the solver that we are using is a modified nodal analysis based approach, which essentially solve this equation at a scale. So essentially what we discussed in terms of the electrical world, so that system is that electrical network can be represented with some matrices to be modeled, and this GC matrix are essentially these are the conductance and capacitance matrix, and Q essentially is a vector of the input power or the heat consumption, heat generation in the system. So with that base for the foundation, which is very similar to other compact thermal simulator, apart from the solver side, the simulator essentially receives your electrothermal specs in terms of the nominal power consumption, or if there's a transient analysis, the power traces, other relevant input, for example, the maximum temperature that you target. In terms of the physical aspects, the platform definition, the floor plan, the dimension of the components, the locations of the chiplets, the number of them, their power consumption, the material. And on the simulation side, the type of simulation, the specific, for example, boundary condition that you have, for example, the environmental temperature, or the phases that are having connection to the air. And then based on this and the type of simulation, either steady state or transient, based on this essential information, the tool essentially creates the network for us, and essentially generate this GC and the cube matrix and vector that we essentially discussed, and solve it with to generate the required output for each type of simulation. It could be either a report, text report, and also thermal heat map, as well as if it is transient, a short video for the behavior during the transient simulation. So the key essentially for supporting the heterogeneity is relevant to the fact that we can support different machine granularity at different layers. If you look into this visual 3D representation on the right side, the fact that you can see that the top node and the bottom node, they have different granularity in terms of the machine. And the way that we are modeling in a compact thermal simulator, so you define some granularity for each layer, and you assign some internal nodes to those per each of those cells that you define, which is shown on the left side with some blue colors. And then the question is, okay, now per each of those nodes, you want to find, okay, the thermal, the heat movement, or the thermal resistance between this node and the adjacent node, which are essentially those boundary nodes or those red colored nodes. It's it's very easy when you have, for example, a grid-based approach. For example, you know the direction and the most adjacent node. But when it comes to a heterogeneous definition of the mesh at different layers, and that's probably where ARTSim essentially has some new features that they can find the nearest point or the nearest connection automatically. So you can define any heterogeneity in terms of the meshing across layers, both in 2D and 3D, and the tool is automatically generates the mesh for you and creates the spice network at the end. So per each of those nodes, we have also some assignments of the power, which will be essentially calculated, and also the thermal capacitor per each of those nodes. I just want to mention that there are some nodes that essentially in this model, you can see those red lines, those red nodes, and some boundary nodes. So that if we look, we can essentially see that some of these nodes are added to the system because the user defines those blue nodes in the system. So at the end of the day, the user is not interested to see the temperature for those other nodes that we essentially see here. So the tool essentially, before parsing the matrix to the solver, essentially goes through a polishing phase that essentially removes all those internal nodes and simplifies all the resistances and combine them as much as possible to reduce the size of the the matrices, input matrices to essentially reduce the complexity of computation. So with that meshing approach and the way of connectivity that we essentially consider now, essentially we can support hybrid meshing, hybrid model. So this is a better representation for the nodal meshing that we essentially have here. So the block model, which essentially you assign a single node per block. It's probably the most simple model, but at the same time the most non-accurate model. As the size of the blocks increases, essentially your model is getting worse and worse. On the other side, there is a grid model that you essentially evenly space the num are assigned the nodes across your layer. This is also probably the most complex approach, because if you have interested in a specific layer for a specific accuracy, you should tolerate the same accuracy for your whole layer. And also it's inaccurate at the boundaries. You can see that there are some nodes that are between different blocks. So the way that these tools deal with this problem is either they are averaging the material properties for those boundary nodes, or they assign the nodes to the block based on, for example, the center node location, which is in both cases inaccurate. But in the hybrid meshing approach, you can, that essentially ARTSim supports, you can assign the nodes, the meshing granularity to each of those functional blocks based on the interest. So if there is a thermal sensitive block and you want to increase the or make a finer mesh, that's possible. If there isn't, there are some places in your chip that it is not of interest. You can reduce the thermal. You can reduce the meshing granularity to have a better compromise on your computation time. The other feature that we are essentially presenting in this in ARTSim is the heterogeneous layer. So the traditional CTMs, the solution for heterogeneity is that they averaging material properties, which means essentially homogenization. For the example that I shown in this figure, say you have a silicon interposed, a silicon bridge inside, for example, your organic substrate. So if you want to do that in conventional CTMs, the way is that the way that they calculate is they average out the material properties of the silicon and FR4 for that specific layer and solve the and essentially do the rest based on this assumption. So that which is not the fact, which is not what we are essentially looking for, the heterogeneous integration. We are interested to see the behavior of this specific bridge inside that FR4 layer. So we have the mechanism that we propose is a heterogeneous layer. So the user can define a heterogeneous layer. So in this heterogeneous layer, the user provides a vertical floor plan in addition to the horizontal floor plan that is always received, which is a prioritized placement order of material within a single layer. Say, for example, in this figure, the silicon has higher priority and can be defined as material with higher priority, and it will replace in other places, therefore, for. And the tool, essentially, the rest is automatic. The tool automatically generates the netlist for us with internally defining layers and combining them to create this heterogeneous layer. And that's probably one of the key features that enables ARTSim to support heterogeneous integration at the extreme. In terms of the solver side, we are presenting also a parallel simulation feature for the solver. So the main or the base solver that we essentially firstly presented in ARTSim 1, it's based on LU factorization with partial pivoting, and which is designed specifically for non-symmetric response systems, which is the case for this kind of uh, systems that we are dealing with. So we on top of that, we essentially support the CPU and GPU acceleration. So the way that it works is that the thermal netlist or the spice netlist that we solve at the end is divided into some subfronts for parallel processing. And on the CPU side, we are using some we execute symbolic and numerical factorization using some of the C-level optimized Python libraries. And also on the GPU acceleration side, we are using some PyTorch tensor operations for massive parallelism in the matrix inversion tasks that we have for solving. The comparison that is shown on the figure on the right side, that's for comparing the performance of the ARTSim base, which has no parallelism, with the new features that are added for CPU multi-threading and GPU acceleration. So we are comparing also, so the black bar shows the COMSOL multiphysics performance for the same meshing granularity. For the same system. This case is a 3D IC case. We will see afterwards, but I just give as an example here. We can see that compared to the baseline, we see between, depending on the meshing that we are using on the ARTSim, we see up to 4 orders reduction in the runtime. While for the GPU accelerated version, we see up to 5 to 6 orders of magnitude improvement. And also this figure also shows the error compared to the COMSOL. We can see that with a relative and acceptable meshing, we can easily have less than 1% error in ARTSim compared to the COMSOL multiphysics, while the complexity is a couple of orders less than FEM tools, which is essentially expected from a compact thermal model. We will dive into the more comparison to the thermal to the other CTMs as well. But the fact is that these parallel features are essential as we essentially moving to heterogeneous integration. When you have a lot of fine-grained structures like microbumps, SIG bumps, the TSVs, either you should so the demand is to essentially model them as accurate as possible, or at least reduce the meshing in a way that we can capture the key thermal features of these kind of components. So the demand is to significantly increase the meshing compared to what we had before. And that's where essentially this parallel solver came into effect. So I probably covered some the key features of the ARTSim, or what we propose in this paper. And in terms of for the rest, I will show a couple of case studies that we have shown the performance of ARTSim based on them. The first case study is 3D IC case. It's a 4-layer 3D IC system. And each layer, we are using the specifications of those functional blocks from MCNC benchmark suit. And the packaging hierarchy is also shown on the left figure. On the top, we have TIM layer, heat spreader. On top of that, it heatsink. And the first 3 layers are TSV based, and the last layer, which don't require TSV. For the reference, the die size here is about 500 by 600 micrometer size. In terms of so here we have shown a couple results on the results of this steady state simulation for one of the TSV-based layers. The figure on the left shows the ARTSim, the heat map that is generated from the ARTSim. The middle one is the console, and the right one is hotspot result. Compared to the console multiphysics, the accuracy is within 1.3%, while, for example, for the same case for console for hotspot, it was 2.1%. It's about 46 times faster compared to the hotspot when we are not including the setup time for the simulation, around 200 seconds compared to 4.3 seconds for a steady state simulation. And it is about 400 times faster compared to the console. And all these simulations are done essentially on a single system for fair comparison. The second case study, I mean, you can see the more details of this in the main paper, but I'm just showing here some of the results. The second case study is on so we wanted in this case study really show the extreme support of heterogeneity in ARTSim. And so it's somehow a hypothetical platform. So it's an Intel EMIB platform. There's a bridge inside the package. But also we're combining this with essentially we're embedding in the bridge some SOI waveguides to essentially make it more heterogeneous in terms of the simulation platform. The SOI waveguide is that we are using here is a rectangular silicon core with silicon dioxide cladding. The two diodes are connected using microbumps to the substrate, and here is the results of the thermal maps that we get from ARTSim and COMSOL. So we didn't include other compact simulator given the lack of support for them for this specific case. So the accuracy is less than 0.27% maximum error, so node-to-node comparison compared to COMSOL as an FEM2. And another probably observation from this result is the robustness of the tool. So we can successfully capture this localized thermal effect of these embedded waveguides as shown on the top figure, which is essentially almost impossible with conventional CTMs. The third case is a TSMC InfoPop integrated fan-out package-on-package platform. So this is a hybrid integration platform that essentially shares some features of the 3D wafer level fan-out packaging and some package integration conventional approaches that we have. So the hierarchy of the packaging is shown here. We have some TIVs adjacent to the chiplet, connecting the embedded die from the bottom side to the to the top mounted chiplet with some microbumps. The floor plan and the floor plan of these two chiplets that we are simulating here is shown here. The chiplet one is a processor. It's based on the features of Alpha v6 architecture, and the chiplet 2 is a DRAM. It's a 5-block control memory array that we are simulating here. And the size of the die is much larger here compared to the previous simulations. It's the order of 16 by 16 millimeter size. And here is the result for both ARTSim and COMSOL. So So the top side is for one chiplet, and the bottom two figures are for another chiplet. Um, the right ones are the console, and the left figures are the ARTSim results. The accuracy in this case was maximum 1.17% error compared to the console. Essentially for node-to-node temperature comparison. Another feature probably another observation that we have from this specific case study was that is the higher resolution that we can expect in terms of the thermal maps that we get from ARTSim. You can see on the figure on the bottom left side that we capture the thermal interaction between the chiplet logic blocks and the high density microbump array under this. So it's a small lighter colors on the floor plan of that layer is essentially the effect of the microbump array that connecting from the top. So the tool essentially, based on the meshing that you define, can capture at this high resolution, and there's the effects. So with that, so the future, so there are a couple of things that we can think for improving this work and working probably at the same time. Future research directions that we can have. On the solver side, we can essentially, of course, we're always looking into more capable solutions based on, for example, it could be ML-based. Sometimes this work also can be extended to some thermal prediction tool rather than just solving the thermal behavior. The other feature is automating the CAD integration. That's probably one of the key to industrial essentially adoption of the work. Supporting a standard EDA formats for layout package like a GDS2 and the physical die that MCM file for the layout, or the .brd file typically supported for the board. Automated netlist extraction, so the direct translation of essentially what the user provides as a physical geometry into the thermal netlist based on that. So these are probably some of the works that some of the extensions of some of the possible venues that this work can be extended. So with that, so the heterogeneous integration is essentially becoming the reality this work nowadays. This requires essentially reconsideration of our EDA tools, design methodologies, and thermal part is a key to that. ARTSim which stands for a robust thermal simulator. Supports heterogeneous integration at the extreme. It provides FEM level accuracy with the speed and flexibility required for design space exploration that we require for designing 2.5D and 3D at the earliest stages of the design. And also the tool has some features that not only can be used for thermal modeling of the system, but also can be a handful and useful tool for designing a new package, given the features that it has for supporting heterogeneity. So with that, I'm open to all the questions that you may have, and thank you for your attention.
Thank you, Yousef, for a very interesting talk. So we have a few questions already in the Q&A. If you have questions, please put them there, but let's go over the ones that are already there. So the first one, in the simulation specs, are there many solver types for electrothermal simulation solvers? Is that just like SPICE and we can reuse current circuit simulators?
Yeah, so if the question is we are supporting multiple solver, we are supporting three type of solver, but if you have your own solver and you think it is more capable, yes, of course it's possible to parse the matrices to your solver and solve it at the end with the specific solver that you have.
Yeah, and just to alternate a little bit, so I'll ask a question. So steady state versus transient simulations, how do you view those two for thermal? So in other words, yeah. So I think you're mostly doing steady state, right?
Yeah, so we are supporting both. I mean, I haven't included the result for the transient because it's a little bit difficult to present. Uh, but we support both. In the paper, you can see the post transient and the steady state result. The accuracy is the same. Both we can achieve less than 1% error. Um, the if you're asking about the tool features, it supports both of them. But if you're asking about in general, what is the difference? Uh, in the steady state, typically you're interested uh, in the in the long run simulation of the system to find the maximum worst case scenario in the long run of the system. But in the transient, you're typically looking for some some transient behavior for to find the thermal hotspot of the system to see the worst cases that can happen. Sometimes that cannot be seen uh, in your uh, in your long run time of the system, which is typically is not about the uh, uh, which is essentially both of them are a requirement for reliable system analysis.
Okay. Next question online. So it's about the compact thermal models. So did you use algorithmic macro modeling or model order reduction to create models to speed up thermal simulation?
So we are using model order reduction for the for our solver, but it also uses, as I mentioned, it uses divides essentially the netlist to subnet lists to essentially parallelize this mechanism.
Yeah, and how does this affect the trade-off between accuracy and simulation speed, I guess?
Uh, yeah, so it depends on the case because it really depends on how the matrix shape and the sparsity where the sparsity is located. But in majority of the cases that we have studied, um, the performance at the end is acceptable level. Less than 1% error can be achieved.
Okay. Okay, then maybe let me ask a question just to alternate. So you mentioned already multiple solvers. How about the other tools in the kind of ecosystem? So performance, simulator, power simulator, which are basically the inputs into your thermal simulator. How how do you interface to kind of those?
Yeah. So at this point, the tool, um, as I mentioned, receiving the information as a text files, very similar to what Hotspot does. Uh, we are working on the standard formats acceptance of the inputs, like for example def files or standard formats for receiving the power files, for example the power input files, the standard power input files that the industry works with. Um, but at this point, it's just the text-based input that the user can provide with a specific standard that we define in our library. To how to define these text files, at which format essentially the tool can accept them, but planning for better interface with the standard EDA tools, like on the power side, and as well as the physical CAD models.
Okay. Another online input question. What are embedded waveguides and why do they have thermal effects?
So these waveguides, the this essentially some you can consider as an optical interconnect in your system, and the reason that they are essentially have a thermal effect is that they have a specific power associated with them, which typically is very high power density compared to the electrical interconnect. And the reason that we have integrated that in our silicon bridge, that's just a case to show. I mean, I'm not sure that Intel does that or not, but the reason we essentially went for this extreme heterogeneous integration is just to show the capability of the tool. We are not we hadn't any other purpose apart from that. But the reason that the thermal behavior of this waveguide is important because they are not using that much low power. Even if the scale of the total power is low, the density is not low. So that's the power density is probably one of the key factors when we are working on the thermal side.
Okay. Another question online, and this is related to your last slide, I guess, on the use of machine learning to optimize large-scale transient thermal simulations. And, basically, I'm not sure, maybe they want a little bit more details there, but then there is another question, I mean, related, if you can use machine learning for large-scale transient thermal simulations, can you then do the same for circuit simulations, transient circuit simulations, I guess?
Yeah, I mean, I think it's vice versa. We are borrowing from the circuit works. There are a lot of works on the ML based spice solvers that we are looking into to get ideas and work on them. But on the thermal side, it's more of a from the ML essentially perspective, it's more useful to use your ML approaches for thermal prediction rather than using the ML for more efficient solving the matrix. Given that you have a lot of access to you can generate infinite amount of data that is essentially required for learning the model, for training the model. So you can define any sort of random number of, for example, layers, random number of blocks, random assignments of the power, and then you have any amount of data available for training your model. Of course, you need to have some ranges for each of those features, for each of those parameters. But the bottom line is that I think if ML is useful here, is more for prediction rather than for helping on solving the more on the solver side.
Okay, I guess one more question from online, which again is a little bit too open-ended, but how does the VLSI architecture and vertical floor plan affect the thermal map?
So say I'm just giving an example. Say for example, you have a TSV in your layer, and the TSV has some pads on the both sides. Say for example, aluminum pads on the bottom and top. If you look into from so typically the pad size is larger than your TSV size. And if you look from the top side, you just see that there is, for example, pad. And the assumption is that from the top to the bottom, essentially across this layer, this is the thickness of that copper or aluminum or aluminum layer. But when you're vertically looking into the system, you see that okay, there is some other components. It's not just a pad from the top to the bottom. There is a small TSV that connects these two pads. So this vertical program help you to understand, first of all, the material properties across the vertical dimension and also their sizing. So if it is, for example, TSV, and when you look on the vertical sides, you can see essentially the dimensions of those, the widths, and then based on that, the thermal model is significantly accurate.
Okay, so I guess we are getting, there is one more question. What are the key challenges in dynamic, I guess what we call transient thermal thermal management for 3D ICs? I guess this is a little bit orthogonal to the simulator, but yeah.
The key challenge probably is the fact that it's not like electrical domain that you always expect that in your interconnect, you have an interconnect and most of the current essentially flow through that interconnect. In thermal side, even though you know, for example, your main pass, which is your main the less thermally resistive pass or the most heat conductive pass. The challenge of essentially modeling the transient model of a electrical of a system is that the flow is not always based on your pass. There are always lateral movement. And this lateral movement is not, the size of this lateral movement is not easy to predict. And also, another challenge is that in electrical domain, you easily can find the time or the time scale or the period for example, passing a signal. You know exactly when you from the start point, from the end point, how much delay you expect. And this time constant that you have in your electrical domain is not easily translated to your thermal domain. It's very difficult that if you, for example, turn on a specific, if you have dynamic voltage and frequency scaling in your system, and if you start, for example, high performance computation in, for example, one side of the chip, it's very difficult to understand when this happens. Essentially, this effect comes into, for example, a block that sits on the other corner of the chip. So probably these two are the key challenge, this different understanding how the time constant in electrical and thermal domain are related to each other, and also the fact that the thermal pass and or the heat movement or heat flow in the system is not a single dimensional behavior. So that's probably, these two probably are the key challenges when you want to have a transient simulation of your system.
Okay, to respect everyone's times and schedules, let's thank Yousef, and we are done, and we are looking forward to having you on the next, webinar, Best of TVLSI webinar. Thank you, Yousef.
Thank you.
Yeah, good luck. Bye.
Thank you. Thank you all for joining.
Goodbye, everyone.